Okay, some examples of some graphs dealing again with concavity. And again, we mentioned in the notes that when a function is concave up, it's curving upward. When a function is concave down, it's curving downward. Now in each of these graphs I've got two different functions, but of course one function can curve upward and then change to curve downward. But the question I asked in the notes is what's happening to the derivative when a function's concave up or concave down. Okay, so here I have the original function graphed. Now, if you look at one of a function that's, say, concave up, for example, we can kind of think about what's happening to the derivative. Okay. Well, right here, for instance, just pick a point on the graph. The slope's negative, right? The graph is sloping downward, so the derivative is negative. And it's still negative as I move to another point a little bit further to the right, and so forth. But what you see is that if a graph is concave up, the derivative has to be increasing. Okay, and that's important. See, a function can decrease and increase. It can do either one and still be concave up. But the graph is, and in fact it is doing both here. It's decreasing for a while and then increasing for a while. But concavity doesn't have to do directly with decreasing or increasing. It has to do with how the derivative is changing. So, here, for example, we see that the derivative is negative. Then as we move to the right, it's a little less negative, and then a little bit less negative, more positive, and then eventually the derivative is 0 because the graph is moving horizontally. Slope is 0. And then as we move to the right, the derivative starts to become positive, and in fact it's continuing to increase. Okay? So generally when a graph is concave up, the derivative will be increasing. So here's what we can say. We can say that f prime of x is increasing from left to right. Okay, now remember we're looking at the graph of the original function, but based on the fact that the slope is going up, okay, the derivative has to be increasing. Now of course when a graph is concave down, it's just the opposite. As we go from left to right along this curve, okay, the derivative, for instance, starts positive, but then it becomes less and less positive. Eventually the slope is 0, okay, then it becomes negative and more negative. So for a graph to be concave down, the derivative has to be decreasing from left to right. Okay, so again, that's kind of the idea that a change in the derivative is what determines concavity. Now, what this brings us to, which is on the next slide, is actually how we figure out whether one of these two things is happening. When is the derivative increasing? When is it decreasing? We need to know that if we want to figure out where our function's concave up and concave down. Well, remember too, for something, derivative, for example, for this to be increasing, its own derivative has to be positive. So if the derivative is increasing, it means that its derivative is positive. Okay. Now it seems kind of getting complex here, but remember when the derivative is positive, it tells us the function is increasing. So what does it mean, or what has to happen for the derivative to be increasing? Well, its derivative has to be positive. Okay. So the moral of the story is that whenever the second derivative is positive, it means the first derivative is increasing, which means the function is curving upward, concave up. And similarly here, if I tell you that the derivative is decreasing, it means that its own derivative, its own rate of change is negative. So if the second derivative is less than 0, that means the first derivative is decreasing, which means the original function is curving downward. Okay, so this is the kind of the connection that we're getting to. Increasing and decreasing for the original function has to do with the derivative. Concavity, concave up and concave down, has to do with the second derivative. If the second derivative is positive, the function must be concave up, and whenever the second derivative is negative, the function must be concave down.